Hi, I'm covering section 12.2 today, the fundamental counting principle, or the FCP. So I have been using it in the last section. So let's read the introduction. While carrying a demanding course load, working at a part-time job, and staying up late to hang out with your friends, you have been neglecting good health habits. With no time for exercise, snacking during late night cram sessions, and substituting burgers and fries for mom's home cooking, you have succumbed to the dreaded freshman 15. Maybe it's time to start an exercise program. Assume that you have decided to work out your abs, arms, and cardiovascular system in that order. And your fitness center has 6 machines for abs, 4 for arms, and 8 for cardio. In how many different ways can you vary your workouts using different machines? It is useful to relate a new problem, such as these two problems you have seen before. Whether flipping coins, rolling dice, or selecting outfits, you have seen the same basic pattern. Like when flipping 3 coins, we saw that we can flip 3 coins in 8 ways, 2 times 2 times 2. Or rolling 2 dice, we can roll 2 dice in 6 times 6 equals 36 forms. And I did other examples where we're multiplying the number of ways. So a first thing happens in a number of ways. Then a second thing happens in B number of ways. Then a third thing happens in C number of ways, and so on. So I'm going to, if I cannot copy it, I'm just going to type it. And there it is. Yeah, so I'm going to copy the fundamental counting principle. So what you do is multiply the number of ways. If you have a list of tasks, and each one can be done in a certain number of ways, we multiply the number of ways. Okay, so you want to perform a series of tasks, and the first task can be done in A ways. The second can be done in B ways. The third can be done in C ways, and so on. Then all the tasks can be done in A times B times C, and so on and so forth, ways. Okay, so let's do this exercise, number 1, about the number of ways. Yeah, there are going to be times when a tree diagram becomes impractical. If we have 6 ab machines, 4 arm machines, and 8 cardio machines, how many different workouts can we have if we use one machine from each group? So we have 6 ab machines, 4 arm machines, and 8 cardio machines. So we can have, or you can have, so 6 times 4 times 8. You can have a total of 192 different workouts. Okay, so more examples using the fundamental counting principle. We're going to look at number 634, number 1 of 630 on page 634. And it's probably going to take longer to read this problem than to actually solve it. So the board of an internet startup company has 7 members. If one person is to be in charge of marketing and another in charge of research, in how many ways can these 2 positions be filled? So let's suppose that you first select a marketing person. Okay. So that's not if. So we first select the marketing person. For no particular reason, I'm selecting that first. But if you want, you can select first the research person. There are 7 ways to select a marketing person. And once you select the marketing person, there are 6 people left and 6 ways to select a research person. Okay, so the 2 positions can be filled in 42 ways. Okay, so that's going to be in 42 ways because we have 7 ways to select a marketing person and 6 ways to select a research person. So that's going to be 42 ways. Number 6. So this is another one that is going to take longer to read than to actually answer the question. On the same page, we have number 6. Okay, Jorge is using his educational benefits from the Navy to enroll in 4 courses to prepare him for a career as an architect. The courses are design, science, math, and social science. If there are 7 design courses, 5 science courses, 4 math courses, and 6 social science courses that fit his schedule, in how many ways can he select his courses? So let's count them. Okay, so he has 7 choices for design courses, 5 to select science courses, 4 to select math courses, and 6 social science courses. So Jorge can select his courses. In that's 7 times 5 times 4 times 6. That is equal to 840 ways. Okay, so more examples of the fundamental counting principle. So we did problems very similar to this ones by drawing 3 diagrams. Now with the fundamental counting principle, we can answer the questions in 1 line. That's example 3. On page 631. Okay, in how many ways can 4 coins be flipped? You know that each coin can be flipped in 2 ways, head or tail. Yeah, it takes me longer to type. The longest part is actually to type the answer. So each coin can be flipped in 2 ways. So 4 coins can be flipped in 16 ways. So that's 2 times 2 times 2 times 2. And B, in how many ways can 3 dice be rolled? Assuming that the dice are different, and we're also assuming that the coins are different. Yeah, with repeated items, things are a little bit different. So, but we're not going to do the formula for repeated items. So each die can be rolled in 6 ways. So 3 dice can be rolled in 260 ways. So that's going to be 6 times 6 times 6. We can also use slot diagrams for the fundamental counting principle. Kind of what I did with the seating charts. Okay, sometimes special conditions affect the number of ways we can perform the various tasks. A useful technique for solving problems such as this is to draw a series of blank spaces, as shown in the figure below, to keep track of the number of ways to do each task. We call such a figure a slot diagram. So each box will represent the number of ways that we can do each task. So we're doing example 5. That's on page 632. To open your locker at the fitness center, you must enter 5 digits in order from the set from 0 to 9. How many different keypad patterns are possible if? First case scenario. Any digits can be used in any position, and repetition of digits is allowed. So using a slot diagram, we're going to draw a diagram with 5 boxes. There are 5 digits, so each box will represent 1 digit. So we can use any digits in any position, and repetition is allowed. So something like 0, 0, 0, 0, 0 is allowed, or 1, 1, 1, 1, 1. If that's the case, we have 10 digits for each box. And 10 raised to the 5th power is going to be 100,000. So this is 10 to the 5th, or 100,000 different patterns. 100,000 possible keypad patterns. Okay, B, the digit 0 cannot be used as the first digit, but otherwise any digit can be used in any position, and repetition is allowed. Okay, so we have another diagram with 5 boxes. So we know that the digit 0 cannot be used as the first digit. We only have 9 choices left for the first digit. Otherwise, any digit can be used in any position, and repetition is allowed. So for the other 4 digits, we have 10 choices. This is 9 times 10 to the 4th, or 90,000. And part C, any digits can be used in any position, but repetition is not allowed. We have again the 5 boxes. So repetition is not allowed. For the first box, we have 10 choices, but since repetition is not allowed, in the second box, we only have 9 choices. We cannot use whatever we pick for the first one. Next, we have 8 choices, then 7, then 6. So that product is going to be 30,240 possible keypad patterns. And the last part, this is also a short section. The next section is going to be permutations and combinations, so that's going to be a little bit longer. But the first 2 sections in this chapter are not that long. And actually, sections 12.1 and 12.2 could have been done together in as one bigger section, but that's okay. The last topic is handling special conditions. Okay, so we did this problem. So we will now look at a counting situation requiring a slightly more complex analysis than we needed in the previous examples. It's going to be another problem with about seating charts. So I'm not doing the same example in the book. It's going to be about seating charts, but we're going to do the problems on page 636. Okay, assume that we wish to seat 3 men and 3 women. Alex, Bonnie, Carl, Daria, Edith, and Frank in a row of 6 chairs. Answer exercises 35 to 36 using the fundamental counting principle. To apply this principle, first identify the separate tasks involved in making the seating arrangements. Situation 1. In how many ways can we seat these people with no restrictions? Okay, so we know that we have 6 different people. If we use a seating chart with 6 seats, we have 6 ways to select a seat for the first person, then 5, then 4, then 3, then 2, then 1. So that's going to be in that product is 720. So that's going to be in 720 ways. Number 36. In how many ways can we seat these people if men and women must alternate? Okay, so we have this a little bit different. So we're going to draw a seating chart. We actually have 2 situations. So I'm going to separate them. If men and women must alternate. The first situation is that the first seat is taken by a guy, and then is male, female, male, female, male, female. So let's do that. Man, woman, man, woman. And the other situation is that a woman sits in the first place, and then they alternate as woman, man, woman, man, woman, man. Okay, so the first case scenario, that's 3 male, 3 females. Then 2 and 2, and 1 and 1. So that's 3 times 3 is 9, times 2 is 18, times 2 is 36. Times 1 times 1, that's still 36. And situation number 2, there are 3 women, 3 men. And then 2 times 2, and 1 times 1. So that is also 36. We need to add the 2 possibilities. So we can sit them in 36 ways. Not 36, 36 times 2. So we can sit them in 72 ways. And number 37, in how many ways can we sit these people if all the men must sit together and all the women must sit together? So again, we're going to have 2 situations. Okay, I'm going to make this bigger. Okay, so we also have 2 situations. The first situation is that the guys take the first 3 seats, and the ladies take the last 3. And the other situation is that the ladies take the first 3 seats, and the guys take the last 3 seats. Okay, so first situation, let's say the ladies take the first 3 seats, and the guys take the last 3. Second situation, the guys take the first 3 seats, and the ladies take the last 3. Okay, so first we have 3 ladies, then 2, then 1. And we have 3 guys, then 2, then 1. 3 times 2 is 6, times 1 is 6, 6 times 3 is 18, 18 times 2 is 36. And second situation, we have the same product. First, we have 3 guys, then 2, then 1. And 3 ladies, then 2, then 1. It's the same product, that's going to be 36. So we can sit them in 72 ways. So with this, we end section 12.2. The next section is going to be permutations and combinations. That's going to take a little bit longer. So actually, the last 2 might have been the 2 shortest sections in the semester. But we're going to finish the chapter next time. And thank you for listening.